Today we're going to look at mass spectrometry. So I thought it would be good to start with a little recap of what happens in the mass spectrometer. So as you can see, to begin with, we have the sample inlet where our sample is injected into the machine. And the first chamber it's injected into is the ionization chamber. Okay, and it moves from the ionization chamber into the acceleration area. And then from the acceleration area, it will move into the time of flight chamber, so this would be the longest section where the actual time of flight is measured. Okay, so it's just a long chamber, long vacuum. And then finally, at the end of the mass spectrometer, there is the detector that's hooked up to a monitor, a machine where it can get its signal generator and the spectrum is produced. Okay, let's have a quick look at what goes on in ionization. So the simplest way for ionization to happen is electron bombardment. So if an electron hits a sample and the sample becomes positively charged. Okay, our sample then moves into acceleration where all of the particles are accelerated to have the same potential energy. So if we consider the KE, so if KE is equal to a half mv squared, then we know that 2KE is equal to mv squared. Then we know that if 2KE, if they're all at the same potential energy, then if the mass and the velocity have got to equal that energy, we can consider the energy as a constant, then if the mass increases, then the velocity is going to decrease. So as you can see in the diagram, the bigger particle is moving far more slowly towards the detector. Now, this is obviously quite an exaggeration. The particles move through the flight chamber somewhat faster than they're being shown here. This is an example of a low-resolution spectrum obtained from a mass spectrometer. So some points to note. At the bottom, we've got mz, which essentially is the molecular mass. And up the side, we have relative abundance. Now, the most important thing to look for in your mass spectrum is the molecular ion peak. Now, you might look at this and go, oh, the biggest peak there's the one at 31. That must be the molecular ion peak. But we actually call this one the base peak. The molecular ion peak represents the total molecular mass of your sample, and that's going to be the highest peak. So if we look over at the end here, we've got 3 peaks towards the end. We've got one at 59, one at 60, and one at 61. Now the one at 61 is absolutely tiny, so we're going to ignore that one for now. And the peak at 60, this is our molecular ion. Okay, so this represents the molecular mass of our compound. We can see that at 61, we've got a much, much smaller peak, and this one is going to be due to carbon-13. So there must be, because there's a tiny percentage of all carbon atoms are carbon-13 isotope, then it makes sense that for one in every so many, a certain percentage of all molecules are going to have at least one carbon-13 isotope in. It's very unlikely that they'd have 2, which is why you don't see a peak at 62. But the chances of them having carbon-13, just one of them in there, is enough for you to get a little peak. The peak at 59 would be where it's lost 1. So we're looking for something that easily loses the mass of 1, and if it loses the mass of 1, so this is loss of 1. So we're looking for it to lose something with a mass of 1, so this is clearly where it's lost a hydrogen. Okay, so loss of 1 would be loss of a hydrogen. So all of these other peaks are due to fragments. if we consider when the molecule goes into the mass spectrometer and it gets got bombarded with electrons to cause it to become ionized, then the ionization process, the molecule actually starts to break apart and a process called fragmentation happens. So it might lose a hydrogen, but we also get this big peak, this massive peak at 31, which would be the most stable fragment. Now, you don't need to be aware of fragmentation and be able to interpret fragmentation patterns in your example, but it is quite a useful thing to be able to do. If you can see, if its molecular mass is 60, but our most stable fragment is 31, you can start to think about, well, what could 31 be? Well, what has it lost? It's gone from 60 down to 31, so it's minus 29. And you can start to think, well, what could a molecule lose that would add up to 29? So, well, 1 carbon and 3 hydrogens is 15. So if I add on another carbon, that takes me another 12. So that's going to be up to 27. So another 2 hydrogens. And I've lost an ethyl group. So minus 29 would be losing an ethyl group. So you can get a lot of information from the low resolution mass spectrum. Most importantly, we can work out what the molecular mass of our compound is. And by looking at the fragmentation pattern, we can start to build a picture like a jigsaw puzzle of the different pieces that make up the molecule. But I can't definitively say what my molecule is just from its molecular mass, because there might be several combinations of carbons, hydrogens, oxygens, etc., that can add up to a molecular mass of 60. If we consider a few of the possibilities, so I could have, for example, ethanoic acid, which if you add it up is C2H4O2, and that's going to add up as 24 plus 4 plus 32. It adds up to 60. Or I could potentially have 3 carbons, and if I put on some hydrogens and an alcohol group. So I could have propan 1-ol or propan 2-ol. I wouldn't be able to see which was which, but again, if I look it up, I've got C3H9O, which adds up, that's 36 plus 9 plus 16. Sorry, it's not 9, it's 8. 36 plus 8 plus 16 also adds up to 60, and my alcohol group can be on several different positions. We can't, so there could be lots of structural isomers, but there could be many things that add up to a molecular mass of 60, and we can't tell just from looking at the low resolution spectrum. This is where high resolution mass spectrometry comes in. So if you've got a lot of different options of what your molecule can be, something with a big molecular mass, there could be lots of different carbon, hydrogen, lots of permutations, then it's important that you get a really, really accurate figure on what that molecular mass is. Now, high resolution mass spectrometry has a resolution of 4 decimal places. So you can see this is for this spectrum I've got here is for a particularly large molecule. You can see it's got a molecular mass of 921.8960, which is absolutely huge. We're talking like a small protein molecule or something here. So the next question you might ask is, well, where do these 4 decimal places come from? So if you consider that I've got a table here of the actual accurate mass of the different atoms. Now you can see carbon has a mass of 12. Exactly 12.0000, and that's because if you remember when we did the definition of relative atomic mass, everything is given as relative to the atomic mass of carbon, which is given of carbon 12, which is defined as having a mass of 12 grams per mole. And everything else is kind of given relative to that. So you can see hydrogen is pretty much 1, oxygen is pretty much 16, but the numbers they're not whole numbers. They can be given to more decimal places because these are numbers that are based on the mass of a proton and the mass of a neutron and the mass of electrons, and they don't round up to exactly being 12, to being 16 and 14. So there are some decimal places to it. And if we're aware of what the accurate mass of the different atoms are, then we can calculate what the accurate mass of different molecules are. So if I move this ever so slightly, then we can look at a table showing us the accurate MR to 4 decimal places of some different options of molecules, which on the low resolution spectrum would all show up as having a molecular mass of 60. But once we work them out, taking into account the accurate mass of the different atoms, we can add up what the high resolution MR would be. So we can see that if we had a high resolution MR of 60.0211, then that would equate to it being 2 carbons and 2 oxygens and 4 hydrogens. Whereas if the mass comes out as 60.0575, then that would be an alcohol. That's going to be, or an ether. So it's going to have 3 carbons and only the 1 oxygen. And there's even another option which had, with another 4 decimal places, which have got the nitrogen in. So you can see by adding up the accurate mass of the different atoms and getting an MR to 4 decimal places, then by using high resolution spectroscopy, we have a way of definitively saying exactly what molecule is in our sample.